Right, I'm going to use dropping a perpendicular to prove two really useful trig ratios, or trig theorems in fact. We've been talking a lot about right angled triangles, there they are, but what happens if your triangle is not a right angle, if it's some peculiar shape like that? Well, yeah, if it's right angle, then we've got sines and cosines and all sorts of stuff. If it's a general triangle, it's not a right angle. There's no right angles in there, so we can't use sines and cosines. So what you do is you take this point here and you just drop a perpendicular. And then, wow, you've got a right angle triangle there, which I've written in blue. And you've got another right angle triangle here, which I'm writing in red. Excuse me, red. We've got two right angle triangles there, and now we can apply trig ratios to those, and then we can do stuff like adding the angles and figuring out what's going on. So that's why dropping a perpendicular is useful. We need some extra notation here. We need some extra notation. So what I'm going to do here, oops, oh, it's there. So we had this angle theta. We talked about the opposite, the adjacent, and the hypotenuse, of course, but for a general triangle, it doesn't quite work. So you normally have different notation. Let me just draw any old triangle. Here it is. So I'm going to call the points A, B, and C. So A, B, and C, capital letters, are the points, or the vertices, I guess the correct way of calling them is. Vertices, put that in quotes. They're the capital letters, right? Now, the lowercase letters, letters, A and B and C, they are the sides, or the lengths of the sides, lengths. And you don't just label them in any old order, you put that one there, so the lowercase letter A, which is that side there, is the side opposite its angle. So this angle here, A, angle A, is opposite side little a. Angle C, which is in there, is opposite side little c, and angle B, which is here, is opposite lowercase b, like that. Okay, so we've got our triangle there, and what I'm going to do is just use this concept of dropping a perpendicular to show you something quite astonishing. So it's really nice little theorem. This, I'm just going to draw it here. You'll observe there's no such thing as standard form if I've got no right angle. B, A, and C. That's side B. That's side A, because it's opposite A, and this is side C here. So what I'm going to do, I can't use trig on this. I can't use trig at all on this because I've got no right angles. So what I do is I take point B and I drop a perpendicular down there to point P. And that's a right angle, and that's a right angle. And now I'm going to observe, I'm going to observe that I've got two right angle triangles here. That's point B there. I've got two right angle triangles, and I'm going to draw one in blue here. Beautiful right angle triangle, already in the standard form. And I've got this red triangle here, which kind of moves along there. That's a right angle as well, not in standard form because we put the right angle at the lower right. So we'll start with the blue one. Okay, and I'll just pinch that in a little bit. Here's my blue triangle here, which has got a nice right angle in it. It's B, P, A, that's side little c. We haven't got names for any of these. I'm going to call that X. And I've got AP there. I haven't got a name for that. Of course, it's part of this line here is part of this. Is that working? Yeah. Okay, so what's X? Well, that's angle A in there. So you'll remember SOHCAHTOA. We're going to use the sine is opposite over hypotenuse. So sine A, I'll go back to black actually. Sine A equals opposite over hypotenuse, which is in this case is x over c. So x equals, by bringing this c up here, c times sine A. There it is. Now, Well, that's great. Suddenly we've figured out the altitude. We've figured out the height of this triangle. So if you're building a house or something and that's part of a roof, then you know how high it is, which is kind of useful information. So you can work out its area and stuff. Okay, now I'm going to take this red triangle here, which is this one here, the red triangle, and I'm just going to fool around with that and see what happens. So here it is, chump, 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 right angle. What have we got? That's point B up there. That's side A. That's C, and that's that new point P which I constructed out of thin air. So the first thing to do is to translate it, I'll go back to black, into, oh, what a mess. Let me just, seem to have lost my eraser. Is that an eraser? No. Oh, there it is. Ha. Right. I'm going to flip it over and put it into standard form simply because it's easy to think about. See, I'm not drawing it perfectly, but it doesn't matter. So that's point B up there. That's P down there for point. That's C. That's my right angle. That's side A. And this angle here is angle C, or the angle at point C. Oh, and that's X there. So let's work out what let's work out what's, I'll just pinch that in a little bit. Oops. So I'm going to work out what sine C is. Sine C equals opposite over hypotenuse, which is X over A. So X sine C equals X over A. So that tells me sine of C. It's not very neat, that, is it? Let me write that out again. Sine C equals X over A. So that tells me that X, by bringing this A up here, is A times sine C. Well, that's great, but we've got two expressions for X. We've got this one here that we worked out from the blue triangle, which is there, and we've got this one here that we worked out from the red triangle. So we know that they're equal because they both refer to the same thing. They both refer to this side here because I've sort of pasted those two triangles together. So what we need is that what we need to do is to observe that C times sine A equals A times sine C. So I'm just going to write that out. C times sine, they're both X. Yeah. So X, we had two expressions for X. Two expressions for X. So X was equal to A sine C from one of the triangles, and X was equal to C sine A for the other, from the other triangle. I forget which way around they were. One from the red, one from the blue anyway. So that tells me that A times sine C equals C times sine A, which is interesting. So what I'm going to do is take this A down here and write A over sine A, sine A equals C over sine C. Wow, that's nice. And I'm also going to write down another thing as well. I'm just going to write it down, B over sine B. Where does that come from? Well, you'll remember when I had my original triangle, I just casually dropped a line from there to there. But I could have dropped a line anywhere. There's my triangle. I could have dropped a perpendicular. That's not very perpendicular, is it? I could have dropped a perpendicular up here. Okay? And so I could have got the same relationship between the different sides. And besides, it's only what I'm labeling them as anyway. So what we've got here is this beautiful thing here, A over sine A equals B over sine B equals C over sine C. Simply by dropping a perpendicular and wondering how long it is. So A over sine A equals B over sine B equals C over sine C, where A and B and C are the lengths of the sides, and A and B and C are the angles. Okay, so there it is. This is the sine rule. which I think is really, 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 really good. The thing is, trig needs a right angle. If you want to use sines and cosines, you've got to have a right angle in there. And of course, not every triangle is a right angle. You might have some, it might be a kind of funny sort of looking triangle that looks like that. Where are your trig ratios now? Well, you can still use them because you've got this formula here, which is absolutely brilliant. That is the sine rule, and I think it's absolutely brilliant. So I'm going to stop here, and I'm going to use it. I'm going to use it in the next one, I guess.